Welcome to a video on relative extrema. We're going to discuss relative maximums, minimums, critical points, and how to apply the first derivative test and second derivative test. Start out with our definition for relative maximum or minimum. Graphically, what we'll be looking for is high points on a graph or low points, hilltops or valleys for relative maximums or minimums, respectively. Locally, that means for a relative maximum, our function value is largest, at least nearby, on an open interval containing the point x sub 0. For a relative minimum, that means it's going to be the lowest function value nearby, locally speaking. An important concept is that of critical point for us, and that's defined to be a point x sub 0 in the domain of the function such that either the first derivative is 0 or for which the first derivative does not exist. Now, a couple important remarks about the definition of critical point, and also these relate to relative maxes or mins. The function must be defined at a critical point or a relative max or min. You have to be able to plug the number in to the function and obtain a point on the graph for it to be in consideration for it being a critical point or a relative maximum or minimum. Meaning, you can't have a critical point or a relative max or min where a function's graph has a vertical asymptote or a hole. There, the function's not defined. You need to consider those aspects when we're graphing, but we cannot have a critical point or a relative min or max at a point of discontinuity like a vertical asymptote or a hole. This is an important theorem, and we'll see some pictures to illustrate it in just a moment. It says if you have a function defined on an open interval containing the point x sub 0, if you have a relative extremum, meaning a max or min at that point, then it must be a critical point. Or it must be a critical point, and that again means that the first derivative is 0 or the first derivative does not exist at the point. But we have to be able to plug that point in. That point must be on our graph. So we're looking at a high point, relative max, a low point, a relative min, or even if you have a relative max or min, you might be looking at a point for which you have a corner point or a cusp in our graph. Here's some other possibilities for critical points. Now, just because you have a critical point does not mean you're going to have a relative max or min. You could if you have a high point or on your graph, and then again that could be your first derivative is 0, could mean your first derivative doesn't exist at a corner or a cusp, or a low point. But you could also be in a situation where your first derivative is 0, but you don't have a relative max or min. So if you have a cubic type graph, then right at your point you could be going from increasing to increasing or decreasing to decreasing, meaning your function is not going to have a relative min or a relative maximum at that point. Your graph would go, say, down or up on either side of your point. Right, so in this case it goes down to the left, up to the right. In the second case it goes up to the left, down to the right. Lastly, you could have a point which is a critical point. We have a vertical tangent line, but that's neither a local minimum or a local maximum. We'll look at the statement of the first derivative test, and that's going to be something that's going to help us determine whether or not we have a minimum or maximum at a given critical point. And then we'll look at it graphically. So it says that if you have a continuous function which is differentiable and its first derivative is positive to the left and negative to the right, so you're going from increasing to decreasing, then you must have a relative maximum at the point. If it goes from first derivative to the left being negative to positive, that means you're going from decreasing to increasing. You must have a relative minimum. If the sign doesn't change for the first derivative, the last conclusion is that you do not have a relative min or a relative max at that point. Now, let's look at the situation graphically. So we can see here, using Paul Seeberger's applet, that we have a relative max here at nearby -2. It's not right at -2, and also near x equals 1. Now, the first derivative test is going to say that the function's derivative should be going from positive to negative. We can see that. And look over here at the left-hand side, we see the slope of the tangent line, which is the value of the first derivative. It's positive, then becomes 0 right at the top, and then goes to negative. Likewise, going past the relative minimum, it's going to go from decreasing to increasing. The first derivative goes from negative to positive there. Another possibility would be looking at, say, the graph of x cubed. Right at x equals 0, the slope of the tangent line is 0. All right, but going to the left, our graph goes down. To the right, our graph goes up. And that tells us that the first derivative is going from positive to positive. It's staying positive, so we do not have a relative min nor maximum there. Another example would be that for which your graph has a cusp or a corner point. In this case, we have a relative min. The first derivative, though, doesn't exist right at x equals 3 in this case, but our derivative is going from negative to positive, so we have a relative minimum there. Notice again, right at x equals 3, the derivative doesn't exist because the tangent line's vertical. Okay, and the last possibility is that of a vertical tangent line at a particular critical point. In this case, it's at negative 2. Our graph has positive slope, positive first derivative, and then it becomes undefined right at negative 2. And then it remains positive, so it goes from increasing to increasing. So we have neither a relative min nor relative max in that example. So again, the first derivative test is going to be used for determining whether a given critical point is a relative max or a relative min. The other tool we're going to have to test whether a given critical point is relative min or max is the second derivative test. There we need the function's first and second derivative to exist. Graphically, what that means is, say the first derivative is 0 at a given point and the second derivative is negative, meaning locally the graph is concave down, we're going to have a relative maximum. If the first derivative is 0 and the second derivative is positive at our point, then on an interval, the graph must, around that point, the graph must be concave up, in which case we have a relative min. Again, first derivative 0, meaning we have a critical point. Second derivative positive means relative min. First derivative 0, second derivative negative means we have a relative maximum at the point x of 0. If they're both 0, the first and second derivative are each 0, then the test is inconclusive. All right, you may have a relative minimum or a relative maximum there. Now, let's go through the steps for finding a relative minimum, relative maximum. You first want to find all the critical points for your function. That is, find all points for which the first derivative is 0 or for which the first derivative does not exist. All right, but again, your function must be defined at those points. You have to discount any vertical asymptote or hole in the graph. Those points where it's not defined are important for as far as graphing the function is concerned, but we're not going to consider them for critical points and relative maxes or mins. Then next, you're going to determine whether you have a relative max or min, or possibly neither one of those two options, at the critical points found in step 1 by either using the first derivative test or, if applicable, use the second derivative test.